Hello there, and welcome. Tonight I want to take you somewhere very special, somewhere so distant that the light reaching your eyes from this place has travelled for hours across the void of space just to meet you here in this quiet moment. I want to take you to the edge of everything we know, to a world so far away that our sun appears as little more than a bright star in an endless night sky. I want to take you to Pluto, and I want to tell you the story of why its heart glows in the soft reflected sunlight that somehow, against all odds, manages to reach those frozen shores 4 billion miles from home. So settle in wherever you are right now. Perhaps you're lying in bed with the lights dimmed low. Perhaps you are curled up on a couch with a blanket wrapped around you. Perhaps you're simply resting after a long day and seeking something gentle to carry your thoughts away from the worries that tug at your mind. Wherever you are, whatever time it is in your corner of this spinning world, you are welcome here. We're going to take this journey together, you and I, drifting slowly through the darkness between worlds, contemplating the quiet mysteries that exist in the cold and distant reaches of our solar system. And speaking of where you are, I would love to know, if you are enjoying this cosmic journey, perhaps take a moment to leave a comment and tell me where you're watching from tonight and what time it is there. Are you in the quiet hours before midnight? Or have the early morning hours already begun to paint the sky outside your window? Are you watching from a bustling city where the stars are hidden by light? Or from a rural place where the Milky Way stretches overhead in all its ancient glory? Wherever you are, whatever time zone holds you in its gentle embrace, know that we're all connected in this moment by our shared curiosity about the universe beyond our little blue world. And if this journey speaks to something within you, if you find yourself wondering about the mysteries of distant Pluto and its glowing heart, perhaps consider subscribing and liking this video so that we can continue to explore the cosmos together in nights to come. Now let us begin with a question. It is a question that might seem strange at first, a question that perhaps you have never thought to ask, but one that has captivated scientists and dreamers alike ever since we first saw Pluto clearly for the first time. The question is this: why does Pluto's heart glow? You see, when the New Horizons spacecraft swept past Pluto in the summer of 2015, sending back images that would forever change our understanding of this distant world, one feature immediately captured the imagination of everyone who saw it. There, sprawled across Pluto's surface like a valentine from the edge of the solar system, was a massive heart-shaped region, bright and distinct against the darker terrain surrounding it. Scientists named it Tombor Regio, after Clyde Tombaugh, the young astronomer who first discovered Pluto in 1930, but to most of us, it simply became known as Pluto's heart. And here is where the mystery deepens, where the question becomes something more than mere curiosity. That heart does not simply exist as a feature on Pluto's surface, the way a mountain range or a crater might exist on our own moon. No, Pluto's heart glows. It catches the faint sunlight that reaches those distant shores and reflects it back into space with an unusual brightness. An ethereal luminosity that seems almost impossible for a world so far from the warming embrace of our star. It is a question that might seem simple at first, a question about reflected light and surface composition. But the more scientists looked into it, the more they realized that something beautiful and unexpected was happening on that frozen world. What if, just maybe, the glow of Pluto's heart was telling us something profound about how worlds work at the edge of darkness? What if that gentle luminosity was the result of processes we had never imagined? Cycles of ice and atmosphere and light that danced together in the cold silence of the outer solar system. What if Pluto, this small and distant wanderer that was once dismissed as not even being a proper planet, was actually showing us one of the most beautiful phenomena in our entire cosmic neighborhood? These are the questions we will explore together tonight, gently and slowly, as the hours drift past like clouds across a moonlit sky. We will not rush. We will not hurry toward answers as though they were destinations to be reached and left behind. Instead, we will let the journey itself become the purpose, letting the wonder of each discovery settle into our minds like snow falling softly on a winter landscape. The answers are beautiful, yes, but so is the asking, so is the contemplation, so is the simple act of turning our thoughts towards something vast and mysterious and infinitely peaceful. To understand why Pluto's heart glows, we must first understand Pluto itself, And to understand Pluto, we must first understand just how far away it truly is. This is not an easy thing to grasp, not really. Our minds evolved on the African savannas, learning to judge distances to the nearest watering hole or the closest predator, not distances measured in billions of miles. But let us try, you and I, to stretch our imagination across that incomprehensible void, to feel just how alone and how far away Pluto truly drifts in its long, slow orbit around the Sun. If you were to get in a car right now and drive toward Pluto at highway speeds, never stopping for fuel or rest, driving day and night at 60 miles per hour, it would take you over 6,000 years to arrive. 6,000 years. Think about that for a moment. Let that number settle into your consciousness like a stone sinking slowly into still water. 6,000 years ago, humans had only just begun to build the first cities along the rivers of Mesopotamia. Writing had not yet been invented. The pyramids of Egypt would not be constructed for another 1,500 years. If someone had started driving toward Pluto at the moment humans first began to cultivate wheat and barley in the fertile crescent of the Middle East, they would still not have arrived by now. They would still be driving through the darkness somewhere beyond the orbit of Neptune, with the faint light of the sun barely visible behind them. Or consider it another way. Light, the fastest thing in the universe, travels at 186,000 miles per second. A beam of light leaving the surface of the sun right now would reach Earth in about 8 minutes, warming your face if you were standing outside on a sunny day. That same beam of light would take over 5 hours to reach Pluto. 5 hours of traveling at the speed of light, and still the journey continues. When you look at images of Pluto, you are seeing light that left the sun hours ago, traveled across billions of miles of empty space, bounced off that frozen surface, and then traveled all the way back to be captured by our telescopes and spacecraft. The light in those images is ancient by the time it reaches us, a messenger from a world so far away that the very concept of distance begins to lose its meaning. And yet, somehow, Pluto is still part of our solar system. It is still bound by the gravity of our sun, still tracing its long elliptical orbit around the same star that warms your face and grows your food and paints your sunsets in shades of orange and red. Pluto is distant, yes, impossibly distant, but it is not separate from us. It is part of the same cosmic family, born from the same swirling disk of gas and dust that gave rise to Earth and Mars and Jupiter and all the other worlds that orbit our yellow star. In a very real sense, Pluto's our cousin, our distant relative, a member of our household who happens to live very, very far away in a cold and lonely corner of the cosmic estate. This is the first thing we must understand about Pluto's glowing heart, the light that makes it glow, the light that reflects off its icy surface and travels across the solar system to reach our eyes, comes from the same sun that rises over your horizon every morning. The same nuclear fusion that warms your skin on a summer day sends a tiny fraction of its light streaming outward into the darkness. And some of that light, a vanishingly small amount, eventually reaches Pluto and falls upon its heart. The glow we see is not some mysterious internal luminosity, not some unknown source of light deep within Pluto's frozen core. It is our own sunlight, travelling impossibly far and then reflecting back to us from a surface of ice and frozen gases that catches the light in beautiful and unexpected ways. But what is it about that surface, about the ice that forms Pluto's heart, that makes it reflect light so brilliantly? Why does the heart glow brighter than the darker terrain surrounding it? These are the questions that puzzled scientists when they first saw those stunning images from New Horizons, and these are the questions that have gradually yielded their answers in the years since that historic flyby. The story of Pluto's glowing heart is a story of nitrogen and methane and carbon monoxide, of glaciers that flow like honey over millions of years, of atmospheric processes that deposit fresh frost on the surface in patterns we're only beginning to understand. It is a story of ice and light, and the strange alchemy that occurs when you bring them together at temperatures colder than anything we can experience here on Earth. But we are getting ahead of ourselves. The night is long and the journey to Pluto deserves a gradual unfolding. Before we dive into the science of the glow, before we explore the composition of the ice and the behavior of the atmosphere, let us spend a little more time simply appreciating the wonder of this distant world. Let us consider what it means that Pluto exists at all. that our solar system extends so far beyond the familiar orbits of the rocky inner planets and the gas giants we know so well. Let us contemplate the quiet miracle of a world that drifts in eternal twilight, at the edge of the sun's influence, a world that has been circling in silence for billions of years, unknown and unnamed, until human curiosity finally reached out to touch it. Pluto was discovered on February 18, 1930, by a young astronomer named Clyde Tombaugh, who was working at the Lowell Observatory in Flagstaff, Arizona. Tombaugh was just 24 years old at the time, a farm boy from Kansas who had built his own telescopes as a teenager and sent drawings of his observations of Mars and Jupiter to the Lowell Observatory in hopes of getting a job. The observatory was impressed enough to hire him, and they set him to work on a project that had been ongoing for years: the search for Planet X, a hypothetical ninth planet that was thought to exist beyond the orbit of Neptune. The search for Planet X was based on what turned out to be a mistaken calculation. Astronomers had observed that Neptune did not move quite as they expected, and they theorized that the gravity of an undiscovered planet must be tugging on it, affecting its orbit. We now know that these observations were simply errors in measurement, that Neptune moves exactly as it should given the masses of the other planets in our solar system. But the mistaken hypothesis led to a real discovery, because Clyde Tombaugh was nothing if not thorough and determined. He spent months photographing sections of the night sky, taking two images of the same region several days apart, and then carefully comparing them using a device called a blink comparator. If anything in the images had moved against the background of fixed stars, it might be the elusive Planet X. Imagine the patience this required. Imagine sitting in a dim room, hour after hour, day after day, comparing photographs of the night sky that each contained hundreds of thousands of stars. Imagine looking for one tiny point of light that had shifted position, one needle in a haystack of cosmic proportions. But Tombaugh persevered, driven by curiosity and hope, and on that February day in 1930 his diligence was rewarded. There, in images taken on January 23rd and January 29th, was a small point of light that had moved. It was faint, much fainter than anyone had expected Planet X to be, but it was real. It was there, and it was moving in exactly the way a distant planet should move. The discovery of Pluto was announced on March 13, 1930, which happened to be the 75th anniversary of Percival Lowell's birth. Lowell had been the founder of the observatory that bore his name, and he had been the driving force behind the search for Planet X, even though he died in 1916 without ever seeing the discovery completed. The name Pluto was suggested by an 11-year-old girl in Oxford, England, named Venetia Burney, who thought that the god of the underworld would be a fitting name for a planet so cold and distant. The first two letters of Pluto also happened to be Percival Lowell's initials, which seemed appropriate given the history of the search. And so Pluto joined the family of known planets, the ninth and most distant member of our solar system. But Pluto was always a strange planet, if it was a planet at all. From the very beginning, it defied expectations. It was too small, too faint, too different from the other planets to fit comfortably into the categories astronomers had created. For decades, our best estimates of Pluto's size kept shrinking as our instruments improved. Early calculations suggested it might be roughly the size of Earth, but by the 1950s it was clear that Pluto was much smaller than that. By the 1970s, after the discovery of Pluto's largest moon Charon, astronomers were able to more accurately calculate Pluto's mass, and they found that it was only about 1/5 the mass of Earth's moon. Pluto was not the massive Planet X that had been predicted. It was something else entirely, something smaller and stranger, a world that seemed to exist at the boundary between what we call a planet and what we call something else. And then there was the orbit. Most planets in our solar system have orbits that are nearly circular and nearly flat, tracing neat ellipses that lie close to the plane of the Sun's equator. Pluto's orbit is different. It is highly elliptical, carrying Pluto as close as 2.7 billion miles from the Sun at its nearest point, and as far as 4.6 billion miles at its most distant. At certain times in its 248-year orbit, Pluto is actually closer to the Sun than Neptune, though the two planets never come close to colliding, because Pluto's orbit is also tilted dramatically relative to the plane where the other planets orbit. For about 20 years out of every 248, Pluto crosses inside Neptune's orbit, briefly becoming the 8th planet from the Sun before retreating back into the cold darkness beyond. This strange orbit told astronomers that Pluto was not like the other planets. It suggested that Pluto might have originated differently, that it might be a captured object from the outer reaches of the solar system, rather than a world that formed in place along with its siblings. And as the decades passed and astronomers discovered more and more objects in the region beyond Neptune, a new picture began to emerge. Pluto was not alone out there in the distant darkness. It was part of a vast population of icy bodies that orbit in a region we now call the Kuiper Belt, named after the Dutch astronomer Gerard Kuiper, who first predicted its existence in 1951. The Kuiper Belt is like a second asteroid belt, but far more distant and composed of objects made primarily of ice rather than rock. It extends from roughly the orbit of Neptune outward to about 50 times the Earth's distance from the Sun, a vast ring of frozen debris left over from the formation of the solar system. Pluto, it turned out, was simply the first and brightest member of this population that we happened to discover. There are likely thousands of Kuiper Belt objects of significant size, perhaps millions of smaller ones, all drifting in the cold and the dark at the edge of our solar system. And in 2005, astronomers discovered an object in the Kuiper Belt that was actually larger than Pluto, a world we now call Eris, named after the Greek goddess of discord. The discovery of Eris forced astronomers to make a difficult decision. If Pluto was a planet, then surely Eris must be a planet too, and perhaps dozens of other Kuiper Belt objects as well. The definition of what constitutes a planet had never been formally established by the International Astronomical Union, and now it was clear that such a definition was needed. In 2006, the IAU met in Prague and, after much debate and controversy, voted to establish a new definition of planet that would require an object to have cleared its orbital neighborhood of other debris. Pluto, sharing its orbital region with thousands of other Kuiper Belt objects, did not meet this criterion. And so, 76 years after its discovery, Pluto was reclassified as a dwarf planet, a decision that sparked outrage among the public and continues to be debated by some scientists to this day. But here is the beautiful thing about Pluto's demotion, the silver lining that perhaps makes the whole controversy worthwhile. When Pluto was just the 9th planet, it was often overlooked, a small and distant afterthought in a solar system dominated by the grandeur of Jupiter and Saturn. But when Pluto became a dwarf planet, when it became the most famous member of a newly recognized population of icy worlds beyond Neptune, something shifted in how we thought about it. Pluto became interesting in a way it had never been before. It became a representative of an entire region of our solar system that we had barely begun to explore, a gateway to mysteries we had never imagined. And when NASA decided to send a spacecraft to visit Pluto, the whole world paid attention in a way they never would have for a routine planetary mission. The New Horizons mission was conceived in the late 1990s and launched in January of 2006, just 7 months before Pluto's controversial reclassification. The spacecraft was small by planetary mission standards, about the size of a grand piano, but it was packed with instruments designed to study Pluto and its moons in unprecedented detail. It was also the fastest spacecraft ever launched from Earth, leaving our planet at a speed of over 36,000 miles per hour and using a gravity assist from Jupiter to accelerate even further. Even so, the journey to Pluto would take 9.5 years, a span of time that encompasses childhoods, careers, entire chapters of human history. Think about what that means for a moment. When New Horizons launched, smartphones as we know them did not exist. Social media was in its infancy. The world that would receive the spacecraft's images of Pluto would be profoundly different from the world that had sent it on its way. And yet, through all those years, New Horizons kept flying, kept transmitting, kept journeying toward its distant destination. It crossed the orbit of Mars in less than 3 months. It reached Jupiter in just over a year, and then it sailed on into the outer darkness beyond the orbits of Saturn and Uranus and Neptune, beyond the comfortable warmth of the inner solar system, into a region of space that no human-made object had ever explored in detail. If you are still with me, if you're still drifting along on this gentle journey toward the edge of our solar system, I would love to hear what you are thinking. Perhaps leave a comment about what has captured your imagination so far. Is it the vastness of the distance we are contemplating? The patience of Clyde Tombaugh searching for a point of light among millions of stars? The 9-year journey of a small spacecraft sailing through the darkness toward an unknown world? Whatever is resonating with you, whatever is sparking that sense of wonder that makes us human, I would love to know. And if you are finding peace in this exploration, if you are feeling your thoughts becoming lighter and more contemplative as we drift through these cosmic distances together, please do consider liking and subscribing so that we can continue these journeys in the nights to come. Now let us return to New Horizons as it approaches its destination. After nearly a decade of silent travel, the spacecraft began its approach phase in January of 2015. 6 months of preparation and observation lay ahead, 6 months during which the images of Pluto would grow sharper and more detailed with each passing week. At first, Pluto appeared as little more than a bright dot, indistinguishable from any star except for its slow movement against the background sky. But as the weeks passed, the dot grew into a disk, and the disk revealed features, and the features began to hint at a world far more complex and beautiful than anyone had dared to imagine. The first clear images of Pluto's surface arrived in early July of 2015, and they showed something that made scientists gasp with surprise and delight. There, covering a significant portion of Pluto's visible hemisphere, was a bright heart-shaped region that seemed to glow against the darker terrain surrounding it. The shape was so distinctive, so immediately recognizable, that it captured the public imagination in a way that few planetary features ever have. Here was Pluto, the cold and distant outcast of our solar system, wearing its heart on its sleeve for all the cosmos to see. It was as if the universe itself had a sense of poetry, a flair for the romantic, hiding this valentine at the edge of our solar neighborhood where only the most patient and curious explorers would ever find it. The closest approach of New Horizons to Pluto occurred on July 14, 2015, when the spacecraft passed within 7,800 miles of the surface, travelling at over 30,000 miles per hour. At that speed, there was no possibility of slowing down or entering orbit. New Horizons had a brief window of opportunity, just a few hours during which it could study Pluto up close, and then it would sail on into the darkness of the outer Kuiper belt, never to return. Every instrument on board was working at full capacity, gathering data as fast as the onboard computers could record it. The spacecraft's radio dish was pointed at Pluto, not Earth, which meant that for about 22 hours around closest approach, New Horizons was out of contact with mission control. The team could only wait and hope that everything was working as planned, that the small robotic explorer they had sent across billions of miles of space was doing its job faithfully in the cold silence beyond Neptune. And then the signal came. New Horizons called home, confirming that it had survived the encounter and that its recorders were full of data. The scientists and engineers who had devoted years of their lives to this mission hugged and cheered and wiped tears from their eyes, knowing that they had achieved something remarkable. Humanity had reached Pluto. We had sent our emissary to the edge of the solar system and brought back treasures of knowledge that would take years to fully analyze. The mission was a success, and the exploration of Pluto had truly begun. The images that New Horizons sent back were nothing short of astonishing. Pluto was not the dead, cratered world that many had expected. Instead, it was geologically active and incredibly diverse, with towering mountains of water ice, vast plains of frozen nitrogen, and a thin but complex atmosphere that scattered blue light like a distant echo of Earth's own sky. The heart-shaped region, now officially named Tombor Regio in honor of Pluto's discoverer, turned out to be one of the most fascinating features of all. Its left lobe, a vast basin called Sputnik Planitia, was filled with a sea of frozen nitrogen that appeared to be flowing and churning in slow motion, driven by convection currents within the ice itself. Its surface was remarkably smooth, with few craters to be seen, suggesting that it was constantly being renewed by geological processes that scientists were only beginning to understand, and it was bright, so incredibly, unexpectedly bright. The heart of Pluto reflected far more sunlight than the darker terrain surrounding it, giving it that distinctive glow that had captured everyone's attention from the very first images. But why? What was it about this region that made it so much brighter than everything else? What was the secret of Pluto's glowing heart? To answer that question, we must understand something about how light interacts with different surfaces. When sunlight strikes a surface, some of it is absorbed and some of it is reflected. The The percentage of light that gets reflected is called the albedo of the surface, from the Latin word for whiteness. A surface with a high albedo reflects most of the light that hits it and appears bright, like fresh snow on a winter morning. A surface with a low albedo absorbs most of the light and appears dark, like charcoal or asphalt on a summer road. The albedo of a surface depends on many factors: its color, its texture, its composition, the angle at which the light strikes it, and even the microscopic structure of its crystals or grains. Here on Earth, fresh snow has one of the highest albedos of any natural surface, reflecting up to 90% of the sunlight that falls upon it. This is why snow-covered landscapes are so dazzlingly bright on sunny days, and why glaciers and polar ice caps appear as brilliant white features when seen from space. Old snow, dirty snow, or snow that has partially melted and refrozen has a lower albedo because its crystal structure has changed and its surface is less uniform. The bright fluffy crystals of fresh snowfall reflect light in all directions, while the larger, more irregular crystals of old snow absorb more of the light that reaches them. On Pluto, the situation is similar but involves different types of ice. The heart of Pluto is covered not with water ice, like the glaciers of Earth, but primarily with frozen nitrogen, along with smaller amounts of frozen carbon monoxide and methane. Nitrogen ice on Pluto has an extremely high albedo, reflecting somewhere between 60 and 80% of the faint sunlight that reaches it. This is why the heart glows so brightly compared to the surrounding terrain, which is covered with darker materials including water ice, mixed with organic compounds called tholins that give it a reddish-brown color. But the high reflectivity of nitrogen ice is only part of the story. If the ice simply sat there on the surface, unchanging, it would gradually darken over time as cosmic radiation and solar wind altered its chemistry, and as tiny micrometeorites deposited darker material upon it. The fact that Pluto's heart remains so bright tells us that something is actively refreshing the surface, depositing new layers of clean, reflective ice that maintain that characteristic glow. And this is where the story becomes truly beautiful, where we begin to see the intricate dance of ice and atmosphere that makes Pluto's heart such a remarkable feature. Let us pause here for a moment and simply breathe. We have travelled a long way together, from the warmth of wherever you are resting to the frozen edge of our solar system. We have traced the history of Pluto from its discovery by a patient young astronomer to its reclassification as a dwarf planet, to its stunning reveal by New Horizons. We have begun to understand why its heart glows in the dim reflected sunlight that reaches those distant shores. But there is still so much more to explore, so many layers of mystery to gently unfold in the hours ahead. If you're feeling drowsy, if your eyes are growing heavy and your thoughts are becoming soft around the edges, that is perfectly fine. Let yourself drift if you need to. The cosmos will still be here when you wake, and the mystery of Pluto's heart will wait for you with infinite patience, as it has waited for billions of years in the cold silence beyond Neptune. Perhaps let these images settle into your dreams. A vast plain of frozen nitrogen glowing faintly in the starlight, mountains of water ice standing like silent sentinels at the edge of the known world, a small spacecraft sailing ever onward into the darkness, carrying our curiosity and our wonder into regions we may never see with human eyes. Consider the journey we have taken tonight. We started here, wherever you are, in your familiar surroundings with the weight of daily concerns pressing upon your mind. And now, we are 4 billion miles away, contemplating a world made of ice and frozen gases, a world where the sun appears as little more than a bright star, a world that wears its heart on its surface for all the universe to see. This is the gift of human curiosity, the magic of exploration. We can lie in our beds and travel to the edge of everything, carried on the wings of knowledge and imagination to places our bodies will never go. The heart of Pluto glows, because it is made of materials that catch the light and throw it back into space. Yes, but it also glows because of the processes that keep those materials fresh and bright. It glows because of the delicate atmospheric cycles that deposit new frost on the surface, because of the convection currents that churn the ice and bring fresh material to the top, because of the strange and beautiful physics that operate at temperatures hundreds of degrees below zero in the dim twilight of the outer solar system. Understanding this glow has taught us something profound about how worlds work at the edge of our knowledge. and it has revealed a Pluto far more dynamic and interesting than anyone imagined before New Horizons arrived. Pluto sits at the edge of what we call the Kuiper Belt, that vast ring of icy bodies that extends beyond Neptune into the cold depths of space. For most of human history, we did not even know the Kuiper Belt existed. We did not know that our solar system continued so far beyond the familiar planets that thousands or millions of frozen objects drifted in the darkness at distances that boggle the mind. Pluto was discovered almost by accident, a small point of light caught in the crosshairs of a search for something much larger, and for decades it remained the only known object in that region of space. But now we know better. Now we know that Pluto is just the brightest and most famous member of a vast population of icy worlds, each with its own story, its own history, its own secrets waiting to be discovered. What other hearts might be glowing out there in the darkness? What other features might we find if we could send spacecraft to visit the countless Kuiper Belt objects that orbit beyond our current reach? Pluto has shown us that even cold, distant worlds can be geologically active and visually stunning. It has taught us that we should never assume we know what we'll find until we actually go and look. And it has reminded us that the universe is far more creative and beautiful than our limited imaginations can anticipate. The Sun is so distant from Pluto that it provides only about 1/1000th the illumination that we receive here on Earth. If you were standing on Pluto's surface during the middle of the day, the light level would be roughly equivalent to twilight on Earth, that magical time just after sunset when colours fade to grey and the first stars begin to appear in the darkening sky. And yet this dim illumination is enough to light up Pluto's heart, to make it glow with a brightness that stands out even in the faint sunlight of the outer solar system. The ice that covers Tombor Regio is so reflective, so efficient at catching every photon that reaches it, that even this twilight glow is enough to make the feature visible from billions of miles away. Think about what that means for a moment. Light leaves the Sun and travels for 5 hours across the empty void of space. It finally reaches Pluto and falls upon the frozen nitrogen that fills the heart-shaped basin of Sputnik Planitia. Some of that light is absorbed by the ice, converted into tiny amounts of heat that affect the chemistry and behavior of the surface. But much of it bounces back, reflecting off the bright crystalline surface and beginning the long journey back through space. After another 5 hours, that reflected light might reach Earth, where it could theoretically be captured by a powerful telescope and contribute to an image of Pluto's glowing heart. The photons you see in photographs of Pluto's heart have made a round trip of nearly 10 hours at the speed of light, crossing distances that dwarf anything in our everyday experience. And yet those photons connect us to Pluto in a very real way. The light that bounced off Pluto's heart and travelled to Earth carries information about the surface it touched, information about the composition of the ice, the texture of the terrain, the processes that shape this distant world. By studying that light, by analysing its spectrum and intensity and polarisation, scientists can learn about a place they will never visit. A world so far away that even our fastest spacecraft took nearly a decade to reach it. This is the magic of remote sensing, the alchemy of astronomy. We catch the light of distant worlds and transmute it into knowledge, building understanding from photons that have travelled inconceivable distances to meet our instruments. The left lobe of Pluto's heart, the vast basin called Sputnik Planitia, is about the size of Texas. It is filled with frozen nitrogen to a depth of several miles in some places, a sea of ice that flows and churns and renews itself in cycles that span thousands or millions of years. This nitrogen ice is responsible for much of the heart's distinctive glow, reflecting sunlight back into space with an efficiency that keeps the region bright even as darker materials fall upon it from above. The ice is kept fresh by a combination of atmospheric processes and internal dynamics that work together to maintain Pluto's most famous feature in a state of perpetual renewal. The atmosphere of Pluto, thin though it is, plays a crucial role in keeping the heart bright. Nitrogen sublimates from the surface of Sputnik Planitia during Pluto's warmer periods, rising into the atmosphere as a gas and then refreezing as frost when it encounters colder regions. This frost falls back to the surface, depositing fresh, clean nitrogen ice that has a high reflectivity. The process is similar to the way snow falls on Earth, except that on Pluto, The snow is made of frozen nitrogen rather than frozen water, and the temperatures involved are around minus 230 degrees Celsius rather than 0. But the principle is the same. Fresh frozen precipitation renews the surface and keeps it bright. At the same time, convection currents within the nitrogen ice itself work to bring fresh material to the surface. The ice in Sputnik Planitia is not static. It is slowly flowing, driven by heat rising from Pluto's interior and by the differential warming and cooling of different parts of the basin. Where the ice is warmer, it is slightly less dense and rises toward the surface. Where it is cooler, it sinks back down into the depths. This creates giant convection cells, visible in the images from New Horizons as polygonal patterns on the surface of the ice, each cell spanning dozens of miles. The ice rises in the center of each cell, spreads outward across the surface, and sinks back down at the edges, completing a cycle that takes somewhere between 100,000 and 1 million years. This convection has a remarkable effect on the appearance of Sputnik Planitia. By constantly bringing fresh ice to the surface and recycling older, darker material back into the depths, it maintains the high reflectivity of the region even over geological timescales. The surface of the nitrogen ice is constantly being renewed, erasing craters and other features that would otherwise accumulate, and preserving the smooth, bright appearance that makes Pluto's heart glow. In a sense, Sputnik Planitia is like a giant lava lamp made of frozen nitrogen, with blobs of ice rising and falling in slow motion over eons, keeping the surface perpetually fresh and reflective. The right lobe of Pluto's heart is somewhat different from the left. While Sputnik Planitia is a deep basin filled with nitrogen ice, the eastern portion of Tomball Regio is a highland region covered with a different mix of ices and terrains. Here you find rugged mountains of water ice, their surfaces coated with frozen methane and nitrogen that give them a bright appearance. The chemistry is more complex in this region, with different ices interacting in ways that create a variety of surface textures and colors. But the overall effect is similar. The heart as a whole reflects more light than the surrounding terrain, creating that distinctive glow that captured the world's imagination when New Horizons sent back its first clear images. Perhaps you're wondering about the temperature on Pluto, about what it would feel like to stand on the surface of this distant world and look up at the dim sun hanging in a dark sky. The answer is almost beyond comprehension. Surface temperatures on Pluto range from about minus 230 to minus 210 degrees Celsius, depending on whether you are on the day side or the night side, whether you're in direct sunlight or in shadow. These temperatures are so far below anything we experience on Earth that they are difficult to imagine. At these temperatures, nitrogen and carbon monoxide and methane, which we know as gases here on Earth, are frozen solid. Water ice, which we think of as cold, is so far below its freezing point that it behaves like a rock, forming mountains that tower miles above the surrounding plains. If you were somehow transported to the surface of Pluto, you would not survive, of course. The cold would be instantly lethal, and the thin atmosphere would provide no breathable air. But imagine for a moment that you could stand there protected, looking out across the vast plain of Sputnik Planitia with its polygonal convection cells and its gentle slopes leading up to the mountains of water ice at its edge. The sun would appear as a bright star, larger than any other star in the sky but still just a point of light, providing illumination roughly equivalent to twilight on Earth. The sky would be a deep, dark blue, coloured by the scattering of light through Pluto's thin nitrogen atmosphere, and beneath your feet the nitrogen ice would be slowly flowing, churning, renewing itself in cycles that have continued for billions of years and will continue for billions more. This is the landscape that glows in reflected sunlight, the heart of Pluto that captured our imagination and rewarded our curiosity. It is a landscape of profound stillness and incredible age, a world that has been circling in the cold darkness since before life began on Earth, unchanged in its essential nature even as continents drifted and species rose and fell on our distant blue planet. And yet it is also a landscape of continuous activity, of subtle changes that occur over timescales we can barely comprehend, of ice that flows, an atmosphere that rises and falls, and chemistry that slowly transforms one compound into another under the dim light of the distant sun. As we continue our contemplation of Pluto's glowing heart, let us also consider what it means for a world to be so far from the sun and yet still so clearly part of our solar system. The light that illuminates Pluto, faint though it is, comes from the same star that warms our faces and grows our crops. The gravity that holds Pluto in its orbit is the same gravity that keeps Earth circling the Sun year after year. In a very real sense, Pluto and Earth are siblings, children of the same stellar parent, formed from the same primordial cloud of gas and dust that collapsed to create our solar system 4.5 billion years ago. We are connected across that vast distance by the invisible bonds of gravity and light, by our shared origin and our common cosmic heritage. The discovery of why Pluto's heart glows has taught us something important about how worlds work at the edge of our knowledge. It has shown us that even in the coldest, most distant reaches of our solar system, there are active processes shaping the surfaces of worlds in ways we never anticipated. Before New Horizons arrived, many scientists expected Pluto to be a dead, cratered ball of ice, interesting perhaps, but geologically inert. What they found instead was a world of mountains and glaciers and atmospheric hazes, a world where nitrogen ice flows like glaciers and where fresh frost falls from a thin blue sky. The glow of Pluto's heart is a symptom of all this activity, a visible sign that this distant world is far more dynamic and complex than we ever imagined. Consider for a moment how remarkable it is that we know any of this. 100 years ago, Pluto had not even been discovered. 50 years ago, it was just a faint point of light in the most powerful telescopes, a world of which we knew almost nothing except its orbit and its approximate size. 20 years ago, we launched a spacecraft to visit it, knowing that the journey would take nearly a decade and that we might never get another chance to explore this distant world. And now, in the quiet hours of this night as you drift towards sleep, we can contemplate the detailed geology of Pluto's heart, understand the processes that keep it bright, and marvel at the beauty of a world that has been waiting at the edge of our solar system for all of human history, ready to reveal its secrets to anyone patient and curious enough to look. This is the gift of exploration, the reward of curiosity. Every answer we find leads to new questions. Every mystery we solve reveals deeper mysteries beneath. We now know why Pluto's heart glows, but that knowledge has opened up new avenues of inquiry that will keep scientists busy for decades. How exactly does the convection in Sputnik Planitia work? What drives the atmospheric cycles that deposit fresh frost on the surface? How has the heart evolved over billions of years, and how will it change in the billions of years to come? These questions await future explorers, future missions, future generations of curious humans who will carry the torch of discovery forward into times we cannot imagine. For now, let us simply rest in the wonder of what we have learned. Let us appreciate the beauty of a distant world that wears its heart on its surface, glowing softly in the dim reflected light of our shared sun. Let us feel connected to that frozen plain of nitrogen ice, that sea of gently flowing glaciers, that landscape of mountains and valleys and hazes that exists at the edge of everything we know. In the silence of your room, in the quiet of this night, Pluto's heart continues to glow, patient and eternal, waiting for the next beam of sunlight to fall upon its surface and begin the long journey back to Earth. The New Horizons spacecraft that revealed all of this to us is still out there, sailing ever deeper into the Kuiper Belt, exploring new objects and sending back data that continues to expand our understanding of the outer solar system. After its flyby of Pluto, New Horizons was directed toward a smaller Kuiper Belt object called Arrokoth, which it passed on New Year's Day of 2019. Arrokoth turned out to be a contact binary. Two objects that had gently merged into a single snowman-shaped body billions of years ago, preserving a record of the conditions that existed in the early solar system. Like Pluto, Arrokoth surprised us with its complexity and beauty, reminding us once again that we should never underestimate what we might find when we venture into the unknown. New Horizons continues to return data about the Kuiper Belt environment, measuring the density of dust particles and the intensity of radiation in this distant region of space. It is now about 5 billion miles from Earth and receding at a rate of about 300 million miles per year. Eventually, probably sometime in the 2030s, its nuclear power source will no longer be able to provide enough electricity to operate its instruments, and the spacecraft will fall silent. But by then, it will have traveled billions of miles further into the darkness, carrying a small piece of human curiosity and ambition into regions that no human-made object has ever explored. Perhaps you can imagine New Horizons out there right now, a small artificial moon sailing through the endless night, its radio dish occasionally turning back toward Earth to whisper the secrets it has discovered. The images it took of Pluto's heart are stored in the memories of countless computers around the world. But the original data that created those images travelled across billions of miles of empty space, carried by radio waves that spread and weakened with every mile they travelled until they were barely whispers by the time they reached the vast radio telescopes of the Deep Space Network. And yet, those whispers were enough. They carried the information we needed to understand why Pluto's heart glows, to see the convection cells in the nitrogen ice, to measure the composition of the atmosphere, to map the mountains of water ice that ring Sputnik Planitia like silent guardians. This is the nature of exploration in our age. We send small robotic emissaries into the darkness, patient and obedient, following instructions written years in advance and improvised by distant controllers who must wait hours for their commands to reach their spacecraft, and hours more for the responses to return. The human explorers who actually travel to these distant worlds are the scientists and engineers who design the missions, who write the software, who analyze the data that comes back across the void. They explore with their minds what their bodies can never reach, building understanding from faint signals and blurry images that gradually sharpen into clear pictures of distant worlds. And in a sense, you're an explorer too, lying there in the darkness as these words wash over you. You're traveling to Pluto in your imagination, contemplating the glow of its heart from 4 billion miles away, building your own understanding of this distant world from the information that patient scientists have gathered and shared with the world. Your curiosity is the same curiosity that drove Clyde Tombaugh to spend months comparing photographs of the night sky, the same curiosity that inspired the team behind New Horizons to spend decades planning and executing a mission to a world most people had written off as uninteresting. That curiosity is perhaps the most remarkable thing about our species. The quality that has carried us from the African savannas to every corner of our planet and now, tentatively, into the cosmic ocean that surrounds us. Let us take a moment to appreciate how far we have come in our understanding of Pluto. When Clyde Tombaugh discovered it in 1930, all he could see was a faint point of light that moved against the background stars. He could not have imagined the mountains and glaciers and atmospheric hazes that would one day be revealed, could not have known that this distant world wore a heart on its surface that glowed in reflected sunlight. He simply saw a new world, noted its position, and added it to the map of our solar system. The rest would have to wait for future generations, for technologies that did not yet exist, for spacecraft that would not be launched for another 76 years. And now we are those future generations. We live in the time when Pluto has been revealed, when the mystery of its glowing heart has been explained, when we can contemplate the convection cells in Sputnik Planitia and the nitrogen frost falling from the thin blue sky. We are the beneficiaries of centuries of scientific progress, of thousands of curious minds who each contributed something to our collective understanding of the cosmos. Every observation, every theory, every failed experiment that taught us what did not work has led to this moment, when you can lie in your bed and know more about Pluto than all the humans who ever lived before about 2015. This is a kind of miracle when you think about it. The fact that we can know anything at all about a world 4 billion miles away, a world so distant that light takes 5 hours to reach it, a world we have never touched and will likely never visit with human explorers, is a testament to the power of human curiosity and ingenuity. We have reached across the void with our instruments and our mathematics and our patient observations, and we have brought back knowledge that would have seemed like magic to our ancestors. The glow of Pluto's heart is no longer a mystery but a window into the processes that shape distant worlds, a reminder that the universe follows rules we can understand if we are patient and clever enough to discover them. As we prepare to dive even deeper into the science of Pluto's glowing heart in the hours ahead, let us carry with us this sense of wonder and gratitude. Wonder at the beauty and complexity of the universe, which reveals new marvels every time we look more closely at any part of it. Gratitude for the generations of scientists and engineers who built the foundations on which our current knowledge rests, and hope for the future discoveries that await, the mysteries we have not yet solved, the questions we have not yet thought to ask. Pluto's heart will continue to glow for billions of years after the last human has looked upon it, after our species has either spread among the stars or vanished back into the cosmic dust from which we arose. The nitrogen ice will continue to flow, the convection cells will continue to churn, the frost will continue to fall from the thin atmosphere onto the bright surface. The sun will gradually grow brighter over the next 5 billion years until it finally swells into a red giant and consumes the inner planets. But even then, Pluto will likely survive, retreating further from the dying star and preserving its frozen heart in the cold darkness of deep space. There is something comforting in this, something peaceful about the knowledge that the beauty we have discovered will outlast us by such an unimaginable margin. We are temporary, transient, brief flickers of consciousness in a universe that operates on timescales we can barely comprehend. But the things we discover, the knowledge we accumulate, the wonder we feel when we contemplate the cosmos, these are our contributions to the ongoing story of the universe becoming aware of itself. In discovering why Pluto's heart glows, we have added a small chapter to that story, a chapter that will be read by future generations long after we are gone. So rest easy, wherever you are. Let your thoughts drift among the stars as your body relaxes into sleep. The cosmos is vast and ancient and full of wonders we have not yet discovered, but it is not indifferent to us. We are part of it, made of the same atoms that form distant stars and frozen moons, temporary arrangements of matter that have somehow become capable of wondering about their own existence. The glow of Pluto's heart is our glow too, sunlight reflected from a distant world back to the curious eyes that sent a spacecraft to see it. The night continues, and so does our journey. Ahead of us lie deeper explorations of the science behind Pluto's glow, contemplations of what it means for other worlds in our solar system and beyond, and quiet meditations on our place in this vast and beautiful cosmos. But for now, let us simply sit with what we have learned, letting it settle into our minds like snow falling softly on a winter landscape. The heart of Pluto glows in the darkness, patient and eternal, waiting for us whenever we are ready to continue our exploration. And it glows because it is made of ice that catches the light and throws it back into space. Because processes we are only beginning to understand keep that ice fresh and bright. Because even at the edge of our solar system, where the sun is just a bright star in a dark sky, there is enough light to illuminate a world. This is perhaps the most beautiful lesson of Pluto's heart, that even in the coldest, most distant reaches of our cosmic neighborhood, there is light. Faint, yes. Dim compared to what we experience here on Earth, but present, always present. And where there is light, there is the possibility of seeing, of understanding, of wondering at the beauty of the universe. Pluto teaches us that there are no truly dark places in our solar system, no regions so far from the sun that they are hidden in complete blackness. Even at the edge of the Kuiper Belt, even beyond where New Horizons now sails into the unknown, there is enough light to see by, enough illumination to reveal the surfaces of frozen worlds to patient observers. The glow of Pluto's heart is proof of this, a beacon at the edge of our knowledge reminding us that the universe does not hide itself from those who seek to understand it. It may require patience, dedication, and ingenious instruments to see what is there, but the universe rewards our curiosity with revelations of beauty and complexity that surpass our imagination. Think about the journey that light takes to create the glow we see. Photons are born in the nuclear furnace at the heart of the sun, where hydrogen atoms fuse into helium at temperatures of millions of degrees. These photons begin a tortuous journey outward through the dense solar interior, bouncing from atom to atom in a random walk that takes hundreds of thousands of years to complete. Eventually they reach the surface of the sun and stream outward into space at the speed of light, carrying energy and information into the solar system. Most of these photons fly off into interstellar space, never striking anything, destined to travel forever through the expanding universe. But some of them happen to be aimed at Pluto, 4 billion miles away, and after 5 hours of travel through the void, they arrive at that distant world. When a photon strikes the nitrogen ice that covers Pluto's heart, several things can happen. If the photon has the right energy, it might be absorbed by the ice, transferring its energy to the molecules of frozen nitrogen and causing subtle changes in the chemistry of the surface. But if the photon's energy doesn't match the absorption characteristics of the ice, it will be reflected, bouncing back into space in a new direction, determined by the microscopic structure of the ice crystals. the bright, fresh nitrogen ice that covers Sputnik Planitia is particularly good at reflecting light, sending much of the incoming sunlight back into space rather than absorbing it. This is why the heart appears bright compared to the darker terrain surrounding it, which is covered with materials that absorb more of the light that strikes them. The reflected light from Pluto's heart spreads outward in all directions, carrying information about the surface it touched. Some of this light happens to be traveling in the direction of Earth, and after another 5 hours of journey through space, a tiny fraction of it might enter the aperture of a telescope and be focused onto a detector, becoming part of an image of Pluto. The information contained in those photons, the facts about the composition and texture of the surface they reflected from, can be extracted by careful analysis, revealing details about a world billions of miles away. This is how we learned about the nitrogen ice in Sputnik Planitia, how we discovered the convection cells and the atmospheric processes, how we came to understand why Pluto's heart glows. The light from Pluto's heart is incredibly faint by the time it reaches Earth. The inverse square law tells us that light spreads out as it travels, becoming dimmer with distance according to a precise mathematical relationship. At Pluto's distance, the light reflected from its surface is about 1 trillion times fainter than the light of the full moon. Detecting this light requires large telescopes with sensitive detectors, patient observations that accumulate photons over long exposures, and sophisticated image processing to separate the faint signal from the background noise. But it can be done. It has been done. And the results have revealed a world of stunning beauty and unexpected complexity. The images from New Horizons were particularly powerful because the spacecraft was so close to Pluto when it took them. Instead of observing from 4 billion miles away, New Horizons was right there, just 7,800 miles from the surface at its closest approach. At that distance, details as small as a few hundred meters across could be resolved, revealing features that had been completely invisible from Earth. The convection cells in Sputnik Planitia, each spanning dozens of miles, had never been seen before. The mountains of water ice ringing the nitrogen ice plains, some reaching heights of 11,000 feet, had never been glimpsed. The atmospheric hazes layered above the surface like ethereal veils had never been imagined. New Horizons revealed all of this in stunning detail, transforming Pluto from a mysterious point of light into a world as complex and beautiful as any in our solar system. And yet, for all the data New Horizons gathered, there is still so much we do not know about Pluto. The spacecraft had only one chance to observe the planet up close, flying past at 30,000 miles per hour, with no possibility of slowing down or returning. It photographed only one side of Pluto in high resolution, leaving the other hemisphere largely unmapped. It measured the atmosphere and surface at one moment in time, during Pluto's summer when the planet was relatively close to the Sun and its atmosphere was at its thickest. We do not know how Pluto changes over the course of its long year, how the heart's glow varies as the planet moves from perihelion to aphelion in its elliptical orbit. We do not know what lies beneath the surface of Sputnik Planitia, whether there might be a subsurface ocean of liquid water kept warm by radioactive decay in Pluto's rocky core. We do not know how the convection cells in the nitrogen ice have evolved over time, or how they will change in the billions of years to come. These are questions for future missions, future explorers, future generations of curious humans who will pick up where New Horizons left off. There have been proposals for orbiter missions that would circle Pluto for years, mapping the entire surface and observing changes over time. There have been ideas for landers that would touch down on the nitrogen ice and study it directly. There have been dreams of sending humans to the outer solar system, though such journeys lie far in the future if they ever happen at all. For now, we must content ourselves with what we have learned and what we can infer, building our understanding from the data New Horizons gathered during its brief but transformative encounter. If you are still with me on this journey, if you are still drifting through the darkness toward Pluto as these words wash over you, I would love to know what is capturing your imagination. Perhaps you're thinking about the patient journey of New Horizons, sailing for nearly a decade through the void to reach its destination. Perhaps you're contemplating the photons that bounce off Pluto's heart and travel back to Earth, carrying information about a world so distant it seems almost imaginary. Perhaps you're simply resting in the peaceful images of frozen nitrogen plains and mountains of water ice, letting the quiet beauty of this distant world settle into your consciousness as you drift towards sleep. Whatever is resonating with you, consider leaving a comment to share your thoughts. And if you're finding this journey meaningful, if you feel yourself being carried into a state of contemplative wonder by these explorations, please do consider subscribing so that we can continue these voyages together in the nights ahead. We have explored the history of Pluto's discovery, the journey of new horizons to that distant world, and the basic science behind why the heart glows. But there is still so much more to contemplate, so many layers of this mystery to gently unfold as the night continues. Let us turn our attention now to the nitrogen ice itself, that remarkable substance that covers Pluto's heart and gives it that distinctive glow. Let us consider what nitrogen is, how it behaves at the unimaginably cold temperatures of the outer solar system, and why it forms the flowing glaciers and convection cells that make Sputnik Planitia such a dynamic and beautiful place. Nitrogen is one of the most abundant elements in our universe, the 7th most common element by mass in our solar system. Here on Earth, nitrogen makes up about 78% of the air we breathe, existing as pairs of nitrogen atoms bound together in molecules of N2. At normal temperatures and pressures, nitrogen is a colorless, odorless gas that we inhale and exhale with every breath, largely unnoticed and unappreciated. But when nitrogen is cooled to extremely low temperatures, around -210 degrees Celsius at normal atmospheric pressure, it condenses into a liquid. Cool it further, and it freezes into a solid, forming crystals of nitrogen ice. On Earth, we rarely encounter solid nitrogen because our world is so warm. Even in the coldest places on our planet, the temperature never drops anywhere close to the freezing point of nitrogen. But on Pluto, the situation is reversed. The temperatures are so cold that nitrogen cannot exist. As a gas or liquid at the surface, it is frozen solid, forming vast deposits of ice that cover significant portions of the planet. The heart of Pluto, Tombor Regio, is the largest concentration of this nitrogen ice, a reservoir that has accumulated in the deep basin of Sputnik Planitia over billions of years. Nitrogen ice has some remarkable properties that contribute to the glow of Pluto's heart. It is highly reflective, with an albedo that can reach 80% or more for fresh, clean ice. This is much higher than the albedo of the darker materials that cover other parts of Pluto's surface, which is why the heart stands out so brightly in images. Nitrogen ice is also relatively soft and malleable compared to water ice at the same temperature, which allows it to flow under its own weight like a very slow glacier. This flowing behavior is what creates the convection cells in Sputnik Planitia, the polygonal patterns that are visible in the New Horizons images, and that help keep the surface fresh and bright. The way nitrogen ice flows on Pluto is different from the way water ice flows in glaciers on Earth, but the basic principle is similar. When a thick layer of ice accumulates, the weight of the ice on top presses down on the ice below, creating pressure that can cause the ice to deform and flow. On Earth, glaciers flow because the pressure at the base of the ice is high enough to cause the ice crystals to slowly creep past one another, carrying the glacier downhill under the influence of gravity. On Pluto, the nitrogen ice in Sputnik Planitia flows because of convection, driven by heat rising from Pluto's interior. Even though Pluto is so far from the Sun and its surface is incredibly cold, the interior of the planet is warmer. Heat from the radioactive decay of elements like uranium and thorium and potassium, trapped in Pluto's rocky core, slowly works its way outward toward the surface. This heat warms the base of the nitrogen ice in Sputnik Planitia, making it slightly less dense and causing it to rise toward the surface. As the warmed ice rises, cooler ice from the surface sinks to take its place, creating a circulation pattern that slowly churns the entire basin. The ice rises in the center of each convection cell, spreads outward across the surface, and sinks at the edges, completing a cycle that takes somewhere between 100,000 and 1 million years. This convection has profound effects on the appearance and behavior of Sputnik Planitia. By constantly bringing fresh ice to the surface, it prevents the accumulation of darker materials that would otherwise lower the albedo of the region. Dust particles from space, organic compounds formed by the interaction of sunlight with atmospheric gases, and other darkening agents fall onto the surface of Pluto, but in Sputnik Planitia, these materials are swept into the ice and carried down into the depths by the convection currents. Fresh, clean nitrogen ice rises to take their place. maintaining the bright reflective surface that makes the heart glow. The convection also erases craters from the surface of Sputnik Planitia, which is one of the reasons the region appears so smooth in the New Horizons images. Elsewhere on Pluto, impact craters from ancient asteroid and comet strikes dot the surface, some of them preserved for billions of years in the cold, geologically inactive terrain. But in Sputnik Planitia, any crater that forms is gradually erased by the flowing ice, its rim softened and eventually swallowed as the convection cells churn and renew the surface. This tells us that the surface of Sputnik Planitia is geologically young, probably no more than 10 million years old at most, a tiny fraction of Pluto's 4.5 billion year history. Imagine what it would be like to watch the convection in Sputnik Planitia in fast forward, compressing millions of years into minutes. You would see the ice rising in great domes at the center of each cell, spreading outward like pancake batter poured onto a griddle, then sinking at the edges where it meets the ice from neighboring cells. You would see craters form from cosmic impacts and then slowly be erased as the ice flows and churns. You would see the surface renewing itself again and again, like the skin of a living creature, maintaining its bright, fresh appearance through cycles of geological activity that have continued since long before the first humans looked up at the stars. Of course, we cannot actually watch this process unfold. The timescales are far too long, the change is far too slow for human perception. Even the fastest changes in Sputnik Planitia would take centuries to become visible, and the full convection cycle takes longer than our species has existed. But we can see the evidence of this process in the patterns on the surface, in the smooth terrain unmarked by craters, in the high albedo that tells us the ice is constantly being refreshed. We can build computer models that simulate the convection, adjusting the parameters until the models match the observations, and we can infer from those models how the ice behaves over timescales we will never witness directly. This is one of the beautiful things about science. It allows us to perceive processes that are invisible to direct observation, to understand changes that occur on timescales far beyond human experience. By combining careful observation with mathematical modeling and physical understanding, we can see the nitrogen ice in Sputnik Planitia churning and flowing, even though the actual motion is far too slow for our eyes to detect. We can understand why Pluto's heart glows, even though the processes responsible occur over millions of years and at distances we can barely comprehend. Science extends our perception into realms that would otherwise be forever hidden, revealing the secrets of the universe to patient and curious minds. The nitrogen ice in Pluto's heart is not pure. It is mixed with smaller amounts of other frozen gases, primarily carbon monoxide and methane, which also contribute to the appearance and behavior of the surface. Carbon monoxide ice, like nitrogen ice, is highly reflective and contributes to the bright appearance of the heart. Methane ice is particularly interesting because it undergoes chemical reactions when exposed to ultraviolet radiation from the sun, producing complex organic compounds called tholins that give much of Pluto's surface its reddish-brown color. Tholins are not found naturally on Earth, at least not under normal conditions. They are a product of the radiation environment of the outer solar system, where ultraviolet light breaks apart simple molecules like methane and nitrogen and allows them to recombine into longer, more complex chains. The resulting compounds are sticky, reddish-brown substances that accumulate on the surfaces of icy bodies throughout the outer solar system. On Pluto, tholins cover much of the terrain outside of Sputnik Planitia, giving the planet its distinctive color palette of whites and reds and browns. The heart appears bright not only because of its high nitrogen ice content, but also because the convection processes keep tholins from accumulating on its surface. As we contemplate the composition of Pluto's heart, we begin to appreciate just how different this world is from the rocky planets of the inner solar system. Earth and Mars and Venus are made primarily of rock and metal, with water ice appearing only in polar regions or as frost on cold nights. But Pluto is made primarily of ice, with rock playing a secondary role as the dense core around which the icy shell accumulated. The mountains of Pluto are made of water ice, frozen so hard at these temperatures that it behaves like rock. The plains of Pluto are covered with nitrogen and carbon monoxide and methane ice, substances that exist only as gases in Earth's warm environment. It is a world of frozen atmospheres and glaciated seas, a world where the very ground beneath your feet would sublimate into gas if you somehow brought it back to Earth. This is the context in which we must understand Pluto's glowing heart. It is a feature on an ice world, made of ices that do not exist on Earth's surface, shaped by processes that are unique to the cold outer solar system. The glow is not like anything we see in our everyday experience, not like the reflection of sunlight off water or snow or any familiar substance. It is the reflection of sunlight off frozen nitrogen, 4 billion miles from the sun, in an environment so cold that our instruments struggle to comprehend it. And yet, for all its strangeness, it follows the same basic physics that governs the behavior of light and ice everywhere in the universe. The laws of nature are universal, applying equally to the frozen plains of Pluto and the warm beaches of Earth. Perhaps this is the deepest lesson of Pluto's glowing heart, that the universe is comprehensible, despite its vastness, despite its strangeness, despite the distances and temperatures and timescales that defy human intuition. The universe follows rules that we can discover and understand. A world 4 billion miles away, made of substances we never encounter in our daily lives, shaped by processes that occur over millions of years, can still be understood by human minds using the tools of science and mathematics. The glow of Pluto's heart is not magic, not miracle, not mystery beyond our comprehension. It is physics played out on a stage of frozen nitrogen and faint sunlight, and we have learned to read the script. As the night continues and your thoughts perhaps grow softer and more diffuse, let these images settle into your mind like seeds planted in fertile soil. Picture the vast plain of Sputnik Planitia, white and smooth, glowing gently in the dim twilight of the outer solar system. Picture the polygonal convection cells, each one larger than a major city, slowly churning as ice rises and falls in cycles that span hundreds of thousands of years. Picture the mountains of water ice at the edge of the basin, their peaks dusted with methane frost that catches the faint sunlight and scatters it back into the black sky. Picture New Horizons sailing past, a small machine far from home, capturing images that would change our understanding of this distant world. And picture yourself, lying wherever you are, connected to all of this by the simple fact of your curiosity. You're a consciousness that has arisen in this universe, a brief arrangement of atoms that has somehow become capable of wondering about frozen worlds at the edge of the solar system. Your existence is no less remarkable than the glow of Pluto's heart, no less beautiful than the convection cells in Sputnik Planitia. You're the universe becoming aware of itself, contemplating its own wonders through the lens of a human mind. This is perhaps the greatest mystery of all, greater even than the glow of distant moons and planets, that there is something rather than nothing, that consciousness exists to perceive and wonder at the beauty of creation. Let this thought be a comfort as you drift towards sleep. The universe is vast and ancient and full of wonders, and you are part of it. The same atoms that formed in ancient stars that swirled together to create the sun and its planets, that make up the frozen nitrogen of Pluto's heart, also make up you. We are all stardust, temporarily organized into patterns that can think and feel and wonder. When you look at images of Pluto, you are the universe looking at itself, admiring its own handiwork, marveling at the beauty it has created through billions of years of patient cosmic evolution. The atmosphere of Pluto, thin as it is, plays a role in the story of the glowing heart that we have only begun to appreciate. When New Horizons swept past that distant world in the summer of 2015, it looked back toward the sun and captured something extraordinary. Pluto silhouetted against the light of our star, its atmosphere glowing with an ethereal blue haze that extended hundreds of miles above the surface. This backlit view revealed layers upon layers of atmospheric haze, delicate veils of frozen particles suspended in the thin nitrogen air, scattering blue light in much the same way that Earth's atmosphere creates our own blue skies. It was a moment of profound beauty, a reminder that even at the edge of our solar system, the interplay of light and atmosphere creates effects that stir something deep within us. The atmosphere of Pluto is incredibly thin by Earth standards, with a surface pressure about 100,000 times lower than the air pressure at sea level on our planet. If you tried to breathe Pluto's atmosphere, you would find it utterly inadequate, a vacuum for all practical purposes, and yet this wisp of gas, this barely there envelope of nitrogen and methane and carbon monoxide, has profound effects on the appearance and behavior of Pluto's surface. It is the medium through which sunlight must pass to reach the heart below, and it is the mechanism by which fresh frost is deposited on the bright plains of Sputnik Planitia. Understanding the atmosphere is essential to understanding why Pluto's heart glows with such distinctive brightness. The atmosphere of Pluto is not constant. It swells and contracts as the planet moves through its long elliptical orbit around the Sun. When Pluto is closer to the Sun, at the point in its orbit called perihelion, the increased warmth causes more nitrogen ice to sublimate from the surface, thickening the atmosphere. When Pluto is farther from the Sun, at aphelion, the atmosphere cools and much of it freezes back onto the surface, leaving only the barest trace of gas. Pluto reached its most recent perihelion in 1989, and when New Horizons arrived in 2015, the atmosphere was still relatively thick by Plutonian standards, benefiting from the warmth of the planet's closest approach to the Sun. In the decades and centuries to come, as Pluto recedes toward aphelion, the atmosphere will gradually collapse, freezing out onto the surface in patterns that may significantly alter the appearance of the heart. This seasonal cycle of atmospheric expansion and collapse is one of the key processes that keeps Pluto's heart bright. As nitrogen sublimates from the warmer regions of Pluto's surface, it rises into the atmosphere and is carried by winds to cooler regions, where it refreezes as frost. Sputnik Planitia, the left lobe of the heart, sits in a deep basin that acts as a cold trap, attracting nitrogen frost from the atmosphere and accumulating it over time. The constant deposition of fresh, clean nitrogen ice maintains the high albedo of the region, counteracting the darkening effects of cosmic radiation and the accumulation of tholins. In a sense, the heart glows because it is constantly being renewed by nitrogen snow falling from Pluto's thin blue sky. The blue color of Pluto's atmospheric haze comes from the same physical process that makes Earth's sky blue, the scattering of sunlight by small particles. When light encounters particles that are much smaller than its wavelength, it scatters in a way that preferentially affects shorter wavelengths, making blue light scatter more than red. This is called Rayleigh scattering, and it is responsible for the blue color of clear skies on both Earth and Pluto. On Earth, the scattering particles are the nitrogen and oxygen molecules that make up our atmosphere. On Pluto, the scattering is caused by tiny particles of tholin haze, organic compounds formed when ultraviolet light breaks apart methane molecules in the upper atmosphere and allows them to recombine into more complex structures. These tholin particles form high in Pluto's atmosphere and slowly drift downward, creating the layered haze structure that New Horizons observed. As they fall, they scatter blue light back into space, giving Pluto's atmosphere its characteristic color when viewed from certain angles. Eventually, the particles reach the surface, where they contribute to the reddish-brown color of the terrain outside Sputnik Planitia. But within the heart itself, the convection processes and the constant deposition of fresh nitrogen frost prevent these darkening particles from accumulating, keeping the surface bright and reflective. Consider the journey of a tholin particle from its birth in the upper atmosphere to its eventual fate on the surface of Pluto. The particle begins as methane, a simple molecule of one carbon atom and 4 hydrogen atoms, drifting in the thin air high above the frozen plains. Ultraviolet light from the distant sun strikes the methane molecule, breaking the bonds between its atoms and freeing the carbon and hydrogen to recombine in new ways. These fragments join together with nitrogen atoms from the atmosphere, forming increasingly complex organic molecules that eventually grow heavy enough to begin falling. The journey from the upper atmosphere to the surface takes months or years, with the particle drifting slowly downward through the blue haze, scattering light as it goes. When the particle finally reaches the surface, its fate depends on where it lands. If it falls on the dark terrain outside the heart, it joins the reddish-brown layer of tholins that covers much of Pluto, contributing to the low albedo of these regions. But if it falls on the bright plains of Sputnik Planitia, it is quickly buried by fresh nitrogen frost or swept into the ice by the convection currents that churn the basin. Either way, its darkening influence is neutralized, and the heart remains bright. This ongoing battle between the deposition of dark tholins and the renewal of bright nitrogen ice is what maintains the distinctive appearance of Pluto's heart over geological timescales. The haze layers in Pluto's atmosphere extend to remarkable heights above the surface, much higher than scientists had expected before New Horizons arrived. The haze is visible up to about 200 kilometers above the surface, with distinct layers that suggest complex atmospheric dynamics. These layers may be caused by gravity waves, oscillations in the atmosphere similar to the waves that form in Earth's atmosphere when air flows over mountains or other obstacles. As the waves propagate through the atmosphere, they create regions of higher and lower density, and the tholin particles concentrate in the denser regions, creating the visible layering. Imagine looking up from the surface of Pluto, if such a thing were possible, and seeing these haze layers stretching overhead. The sky would be a deep, dark blue, almost black, with the haze layers visible as faint ethereal bands near the horizon. The sun would appear as a bright star, larger than any other star in the sky, but still just a point of light, too small and too distant to warm the frozen landscape below. The light filtering through the haze would be dim and blue, casting soft shadows across the nitrogen ice and giving the entire scene a dreamlike quality. It would be one of the most alien landscapes in our solar system, and yet it would follow the same physical principles that govern the behavior of light and atmosphere on our own world. The interaction between Pluto's atmosphere and its surface creates what scientists call a volatile transport cycle, a continuous exchange of gases between the air and the ground that shapes the appearance of the planet over time. When the sun warms one region of Pluto's surface, nitrogen ice sublimates into gas and rises into the atmosphere. The wind carries this gas to cooler regions, where it condenses back into frost. Over the course of Pluto's long year, which lasts 248 Earth years, the patterns of warming and cooling shift as the planet's orientation toward the sun changes, causing the volatile transport cycle to redistribute ices across the surface in complex ways. This volatile transport is what fills Sputnik Planitia with nitrogen ice and keeps the heart glowing. The basin acts as a permanent cold trap, a region that remains colder than its surroundings because of its low elevation and its position on Pluto's surface. Nitrogen that sublimates from warmer regions is carried by atmospheric circulation to Sputnik Planitia, where it refreezes and accumulates. Over billions of years, this process has filled the basin with miles of nitrogen ice, creating the vast frozen sea that we see today. And because the fresh ice is constantly being deposited on top of older ice, the surface remains bright and reflective, maintaining the heart's distinctive glow. The atmospheric processes that contribute to the heart's glow also create some of the most visually striking features in the New Horizons images. At the edge of Sputnik Planitia, where the nitrogen ice meets the mountains of water ice that ring the basin, the atmosphere creates patterns of frost deposition that highlight the terrain in beautiful ways. The slopes of the mountains are coated with nitrogen and methane frost that catches the faint sunlight and reflects it back into space, making the peaks appear bright against the darker valleys below. These frost patterns change with the seasons, advancing and retreating as the temperature and atmospheric pressure fluctuate, creating a landscape that is never quite the same from one year to the next. If you are still drifting along with me through this gentle exploration, still letting these images of distant Pluto wash over you as you settle deeper into relaxation, I hope you're finding something meaningful in this journey. Perhaps it is the sense of connection to a world so far away, the realization that even at the edge of our solar system, beauty and complexity exist beyond anything we imagined. Perhaps it is the quiet wonder of contemplating processes that occur over timescales we can barely comprehend, cycles of ice and atmosphere that have continued for billions of years and will continue for billions more. Whatever is resonating with you, I invite you to share it in the comments, to let me know what thoughts are passing through your mind as you drift towards sleep. And if this journey is bringing you peace, if you're finding something valuable in these contemplations of distant worlds, please consider liking and subscribing so that we can continue to explore the cosmos together. The atmosphere of Pluto does more than just scatter light and deposit frost on the surface. It also creates optical effects that contribute to the apparent glow of the heart when viewed from certain angles. When sunlight passes through the atmosphere, some of it is bent or refracted by the varying density of the gas, creating a halo effect around the edge of the planet. This atmospheric refraction can make the heart appear slightly brighter than it would if Pluto had no atmosphere at all, adding to the ethereal quality of its glow. The effect is subtle, but it contributes to the overall impression of luminosity that captured the world's imagination when the New Horizons images were first released. There is also forward scattering to consider, a phenomenon where light passing through a medium is preferentially scattered in the forward direction, rather than being scattered equally in all directions. When New Horizons looked back at Pluto from the far side with the sun behind the planet, the forward scattering of sunlight through the atmosphere created a bright halo around the entire world. The heart, with its high albedo and its position on the sun-facing hemisphere, contributed significantly to this glow, appearing as a bright crescent within the overall illumination. These forward scattering views revealed details of the atmosphere that would have been invisible from other angles, showing the full extent of the haze layers and the complex interplay of light and gas that surrounds this distant world. As we contemplate the role of the atmosphere in creating Pluto's glowing heart, we begin to appreciate how interconnected the various components of this world truly are. The surface affects the atmosphere by releasing nitrogen gas when warmed by the sun. The atmosphere affects the surface by depositing frost when the gas refreezes in colder regions. The composition of the ice affects the reflectivity of the surface, which in turn affects how much heat it absorbs from the sun, which affects the rate of sublimation, which affects the thickness of the atmosphere. Everything is connected in a web of feedback loops and interactions that create the dynamic, ever-changing world we see in the New Horizons images. This interconnectedness is one of the hallmarks of planetary science, the recognition that worlds are not just collections of separate features, but integrated systems where everything affects everything else. Understanding why Pluto's heart glows requires understanding not just the composition of the ice, but also the behavior of the atmosphere, not just the albedo of the surface, but also the convection in the interior, not just the current state of the planet, but also its evolution over billions of years. It is a holistic view that reveals beauty and complexity, wonder in the intricate dance of matter and energy that shapes distant worlds. Let us turn our attention now to the light itself, to the photons that travel from the sun to Pluto and back, carrying the information that allows us to see the glowing heart from billions of miles away. Light is the messenger of the cosmos, the medium through which we perceive everything beyond our immediate reach. Every image of Pluto, every measurement of its surface composition, every observation of its atmospheric structure comes to us encoded in light that has traveled across the solar system to meet our instruments. Understanding how light interacts with Pluto is essential to understanding why we see what we see when we look at its glowing heart. Light from the sun travels at about 186,000 miles per second, the cosmic speed limit that nothing with mass can exceed. At this speed, light crosses the 93 million miles between the sun and Earth in about 8 minutes. But Pluto is much farther away, orbiting at an average distance of about 3.7 billion miles from the sun, with its distance varying between 2.7 and 4.6 billion miles depending on where it is in its elliptical orbit. At these distances, sunlight takes between 4 and 6 hours to reach Pluto, arriving much dimmer and weaker than it is here on Earth. The intensity of sunlight at Pluto's distance is roughly 1/1000th of what we experience on Earth, a consequence of the inverse square law that governs how light spreads out as it travels through space. If you were standing on Pluto's surface, the light level would be comparable to twilight on Earth, that magical time just after sunset when the sky is dark but objects are still dimly visible. It would be enough light to see by, enough light to read a book if you held it close, but it would feel profoundly different from the bright sunshine we take for granted on our world. And yet this dim light is enough to make Pluto's heart glow, to illuminate the frozen nitrogen plains of Sputnik Planitia with a soft radiance that can be detected from billions of miles away. The reason the heart can glow so brightly despite the dimness of the illumination is the high albedo of the nitrogen ice that covers it. When sunlight strikes a surface with high albedo, most of the light is reflected rather than absorbed, making the surface appear bright relative to its surroundings. The nitrogen ice in Sputnik Planitia has an albedo of roughly 60 to 80%, meaning it reflects more than half of the light that reaches it. This is comparable to fresh snow on Earth, which is why the heart appears as a bright feature against the darker terrain that surrounds it. The darker regions of Pluto, covered with tholins and water ice, have albedos of only 20 to 40%, absorbing much more of the incident sunlight and appearing dimmer by comparison. The reflection of light from Pluto's surface is not perfectly uniform or predictable. Different parts of the surface reflect light in different ways depending on their composition, texture, and geometry. Smooth surfaces tend to reflect light in a more specular fashion, like a mirror, while rough surfaces scatter light in all directions more diffusely. The nitrogen ice in Sputnik Planitia appears to be relatively smooth on large scales, which contributes to its high reflectivity, but on smaller scales it has texture and structure that affect how it scatters light. The convection cells create subtle variations in the surface that can be detected as variations in brightness, and the edges of the cells, where the ice is sinking back into the depths, appear slightly darker than the centers where fresh ice is rising to the surface. When light reflects from Pluto's surface and travels back toward Earth, it carries information about the surface it touched. By analyzing the intensity, color, and polarization of the reflected light, scientists can infer details about the composition and structure of the surface. Different materials reflect different wavelengths of light preferentially, creating spectral signatures that can be used to identify what the surface is made of. Nitrogen ice has a characteristic spectrum with absorption features at specific wavelengths, as do methane ice and carbon monoxide ice and water ice. By measuring these spectra, scientists were able to map the distribution of different ices across Pluto's surface long before New Horizons arrived, and the spacecraft's close-up measurements confirmed and refined these earlier observations. The journey of light from the Sun to Pluto to Earth is a story of vast distances and patient travel, of photons crossing billions of miles of empty space to carry information about a world we have never touched. Consider a single photon, born in the nuclear furnace at the heart of the Sun, beginning its long journey outward through the solar interior. For hundreds of thousands of years, the photon bounces from atom to atom, slowly working its way toward the surface through a dense forest of matter. Finally, it reaches the photosphere, the visible surface of the Sun, and streams outward into space at the speed of light, leaving behind the star that created it. For 5 hours, the photon travels through the void, passing the orbits of the inner planets, cruising past the gas giants, entering the realm of the Kuiper Belt where countless icy bodies drift in the darkness. Finally, it reaches Pluto and strikes the nitrogen ice that covers the heart, its energy absorbed momentarily by the frozen surface. But the ice does not hold on to the photon's energy. Instead, a new photon is emitted, reflected back into space with slightly less energy than before. This reflected photon begins its own journey, traveling back through the void toward the inner solar system. If it happens to be aimed toward Earth, it might eventually enter the aperture of a telescope and be detected, contributing to an image or measurement of Pluto's surface. The light we see in images of Pluto's heart has made this incredible journey, crossing the solar system twice to bring us information about a world so far away. Every pixel in those images represents countless photons that traveled for hours through the void, bounced off the frozen surface, and traveled back to meet our instruments. The glow we perceive is the accumulated effect of all these photons, their individual journeys combining to create the image of a heart-shaped feature shining softly at the edge of our solar system. There is something profound about this, something that speaks to the nature of observation and knowledge. We cannot travel to Pluto ourselves, not yet, perhaps not ever. The distances are too great, the journey too long, the environment too hostile for human beings. But we can send our instruments, our robotic emissaries, and we can catch the light that bounces off distant surfaces and decode the information it carries. This is how we know about Pluto's heart, how we understand why it glows. We have read the messages written in light, translated the language of photons into knowledge and understanding. The color of Pluto's heart, as captured by New Horizons, reveals additional information about the surface composition. In true color images, the heart appears whitish or pale tan, reflecting the actual appearance of the nitrogen ice to human eyes. But when scientists enhance the colors to bring out subtle variations, the heart takes on a yellowish or slightly peachy hue that distinguishes it from the redder terrain elsewhere on Pluto. These color variations tell us about the different ices present in different regions, with the heart's pale color indicating a relative purity of nitrogen ice compared to the tholin-rich surfaces that surround it. The infrared wavelengths of light reveal even more about Pluto's surface, showing features that are invisible to the human eye. In the infrared, different ices have distinctive absorption features that allow scientists to map their distribution across the surface. Nitrogen ice absorbs strongly at certain infrared wavelengths, as does methane ice, and by measuring the depth of these absorption features, scientists can determine not just where the ices are located, but also their approximate thickness and purity. The heart of Pluto stands out in infrared observations as a region dominated by nitrogen ice, with lesser amounts of carbon monoxide and methane mixed in, exactly as the visible light images suggested. As we consider the light that reveals Pluto's glowing heart to us, let us also appreciate the darkness that surrounds it. Space is not merely empty, it is dark, a void of almost unimaginable blackness that makes the faint glow of distant objects all the more remarkable. Between the Sun and Pluto there is essentially nothing, just the hard vacuum of space stretching for billions of miles. The light that crosses this void is alone in the darkness, a stream of photons traveling in solitude through the emptiness, with nothing to interact with until it finally encounters a surface or an instrument at the other end of its journey. This darkness is the backdrop against which Pluto's heart glows, the absence that makes the presence meaningful. If space were filled with light, if there were no darkness to contrast with brightness, the glow of the heart would mean nothing. It is precisely because space is so dark, so empty, so devoid of illumination, that the faint reflection of sunlight from Pluto's surface stands out as something remarkable. The darkness gives meaning to the light, just as silence gives meaning to sound, and emptiness gives meaning to presence. Perhaps there is a lesson here for us, in our own lives on this bright and busy world. We are surrounded by light and sound and activity, immersed in a constant stream of stimulation that can overwhelm our senses and exhaust our attention. But somewhere beyond all this noise, beyond the atmosphere that scatters our sun's light into blue skies and brilliant days, there is a darkness that stretches to infinity, punctuated only by the faint glow of distant stars and the reflected light of frozen moons. In that darkness, Pluto's heart shines quietly, a reminder that beauty and meaning can exist even in the most remote and empty places. Let yourself drift for a moment, letting go of the details and the data, allowing the images to settle into something simpler and more essential. Picture the heart of Pluto glowing in the darkness, 4 billion miles away, unchanged by your observation of it, unaffected by your thoughts about it. It was there before you were born, and it will be there long after you are gone, glowing softly in the dim twilight of the outer solar system, reflecting sunlight back into the void, with patient indifference to whether anyone is watching. And yet you are watching, in a sense. You are contemplating this distant world, holding its image in your mind, connecting yourself to something vast and ancient and beautiful through the simple act of imagination. If you're still with me as we drift deeper into this contemplation, I would love to hear what thoughts are passing through your mind. Perhaps you're struck by the vastness of the distances we're discussing, the incomprehensible scale of the solar system that contains Pluto and Earth and everything in between. Perhaps you are moved by the delicacy of the processes that create the heart's glow, the gentle cycles of ice and atmosphere that have continued for billions of years. Perhaps you're simply resting in the peaceful images of frozen plains and dim sunlight, letting the quiet beauty of this distant world carry you towards sleep. Whatever is resonating with you, I invite you to share it in the comments before we continue our journey. And if you are finding peace in this exploration, please do consider subscribing so that we can continue to travel together through the cosmos in nights to come. Now let us consider what the glow of Pluto's heart tells us about other worlds, both within our solar system and beyond. One of the beautiful things about studying a single object in detail is that it teaches us principles that apply to many other objects as well. By understanding why Pluto's heart glows, we gain insights into how surfaces reflect light, how atmospheres interact with surfaces, how ices behave at extremely low temperatures, and how geological processes shape distant worlds. These insights help us interpret observations of other moons and dwarf planets and even exoplanets orbiting distant stars.